Good afternoon. I'm Scott Anderson. I'm Principal Geotechnical Engineer with BGC Engineering, and I'm here now to take a couple moments and introduce the SEED lecture for this year. Not the lecturer, but it's especially sweet that the lecturer this year is Professor Frost, who I've had the opportunity to work with over the past several years on the GEAR Association efforts. But I'm here to do some promotion because that's what sponsorship's all about. So I'm promoting BGC Engineering. And I'm also going to take this opportunity to say a few words publicly about Professor Seed. Professor Seed was probably the most influential mentor that I've had. I had the opportunity to spend a couple of years with him. And it wasn't the way that he taught effective stress or 1D consolidation or any of those things. It was his passion for tackling problems that didn't have ready solutions, where there was some data, there was a need, there was enough understanding that something could be pioneered that would be valuable. And it turns out that's in the tagline of BGC Engineering as well. I didn't make up those words on the bottom of the screen for these remarks. They are the principles we operate under at BGC. BGC Engineering is a company of about 750 people. We work internationally, about half in the mining sector, half in the civil sector. We have a world-class laboratory with a lot of focus on liquefaction. And we also have innovation in our DNA. We do a lot of research and development at BGC. We have over 70 internally funded R&D projects going on right now. We spend 3 to 5% of our revenue on R&D. This is an employee-held company. This is money out of our pockets. We recognize that we get greatest innovation when we partner with others, but we're willing to pony up, and we do every year, to innovate and bring forward new approaches to problems. Another thing that I'm really proud about with BGC Engineering, and if I can figure out where the slides are, or if someone could advance for me, oh, there it is, under my hand, is something called BGC Squared. And this is a program within BGC Engineering where a staff member would propose a problem that needs a solution, and BGC, the company, would multiply times that, and we'd go off and do something where we could use the skills that we have to help make the world a better place. And sometimes these are things like K through 12 education, and sometimes these are traveling to Zambia or Bhutan or other places, or using our geophysical skills to look for undisclosed Holocaust historical sites, and to present them in ways that some of you may have seen me talk about before in an augmented reality kind of fashion. So with that, I just want to say thank you for giving to the GI for giving me this opportunity to speak. Thank you for listening. Thanks to Professor Seed for launching me in this direction. And I do also want to close with saying there's 4 of us from BGC here today: Molly Winston, Andrea Lougheed, and Alexa Spersky, and me, Scott Anderson. Please come find us, talk about innovation or something else, and have a spectacular conference. Thanks.
Good evening. My name is Susan Burns, and I'm a professor at Georgia Tech. It's my great honor to be here tonight to introduce my colleague and my great friend, Dr. David Frost. David is an internationally recognized expert in the study and analysis of natural and man-made disasters, spatial information systems, and engineering behavior of soils under static and dynamic loading. David earned his undergraduate degrees in civil engineering and mathematics from Trinity College, Dublin, after which he worked in industry in Ireland and Canada for about 6 years. He then returned to graduate school, where he pursued a master's and ultimately a PhD in civil engineering from Purdue University in 1989. After serving 3 years on the faculty at Purdue, David joined the faculty at Georgia Tech, where he's been for the last 30 years or so. He's currently the Bill and Elizabeth Higginbottom Professor of Civil and Environmental Engineering. David has an extraordinary list of professional accomplishments with hundreds of publications, keynote, plenary lectures, and invited seminars. Perhaps what is most impressive about his work, however, is both the depth and the breadth of his comprehensive approach to study disasters. From work performed at the micro scale to better understand how failures are initiated, to macro scale study of failures. All of his investigations feed to formulations of ways for engineers to build resilience into infrastructure and create management plans for rapid recovery from disasters. While David has built a remarkable research record, I first came to know him as a teacher and a mentor. I can still remember the first conversation we ever had, which was full of enthusiasm and excitement for his recently awarded proposal on image analysis. From that day over 30 years ago through to this day, I have never once seen David's excitement for his work waver. And that translates into remarkable things for the people who work with him in the classroom, as a colleague, and as a mentor. He has an amazing ability to use his enthusiasm to motivate the people around him, to energize students and colleagues, and to promote the very best in people. He draws from what seems like an unending reservoir of energy. He does this to teach and to mentor, and to build and support community. To date, David has advised 56 PhD students, a number which is still climbing every year, and 20 of those students now serve in distinguished academic positions around the world. Similarly, his students who have chosen to go into industry are now leaders in some of our most distinguished geotechnical engineering firms. But David's influence is far-reaching, which is reflected by the fact that several of his former students are working actively as data scientists, working for companies like Amazon, Facebook, and Google, which is a real testament to the innovative work that is being performed by his research group. David's impact on our profession is truly breathtaking. As I reflect on David's career, I clearly see a professor who understood mentoring before academia really even had a framework to describe mentoring. He's been a tireless advocate, promoter, and mentor, not only for his students, or students in the US, but for students around the globe. And that includes countless women and people from underrepresented groups in engineering. He has worked behind the scenes to listen and to deliver wise counsel as needed, and he's incredibly generous with his time. While David's formal mentoring contributions are extensive, I find it even more remarkable because I know he's mentored so many people behind the scenes. He's made huge impact on many, many lives, my own included. But what I would say is David's greatest gift is that he sees the world with different eyes. He brings an intensity of focus to everything he touches, an intensity that combines an ability to see deeply into a problem while simultaneously understanding the macro-scale implications of that problem, as is so clearly reflected in the work his research group performs. I've been in a lot of meetings with David, a lot. I've served on many, many committees with David, and he always brings depth of insight, along with an uncanny ability to place every seemingly intractable problem into a new, manageable context. And what is most striking is that I've seen him do this time and time again, with many challenges that are highly technical, but also challenges that are interpersonal. He is a remarkable communicator and an unparalleled problem solver. In summary, I would like to close with a quote from Dr. Wayne Clough, President Emeritus of Georgia Tech and Secretary Emeritus of the Smithsonian Institution. When speaking about David Frost, Dr. Clough says, "It was my privilege to take courses from Dr. Seed when I worked on my PhD at the University of California in the 1960s, and also to serve as his teaching assistant, where he took the time to help me become a better teacher. The Bolton Seed Medal is indeed a high honor. I always thought that the true genius of Dr. Seed's work was that it was grounded in fundamentals, but concluded with easy-to-use tools for practicing engineers. David Frost has also demonstrated this talent to the benefit of the future of our profession and to the people we serve. I cannot think of a more fitting person than David Frost to be given the H. Bolton Seed Medal." And with that, please join me in welcoming David Frost to the stage.
Well, thank you very much, Susan. I was sitting down there and I was not recognizing the person who she talked about, which made me a little scared, made me think I had come to the wrong room or something. And I definitely very much appreciate those incredibly kind words. It is indeed an incredible honor for me to be invited to give this lecture, and so I'm very excited to do so. The title of my talk is "The Role of Compatibility in Geotechnical Interface Behavior." Okay, so let me start off with a little motivation. And in contrast to many of you in the room here who had obviously the absolute privilege to work directly with Dr. Seed, whether it was in research or taking classes from him, I was never afforded that opportunity. However, I did have one very brief opportunity for interaction, not directly with Dr. Seed, and that was the very first Geo-Conference I went to was in situ 86. And as I sat in the audience as a fresh master's student, there were these two middle-aged gentlemen were in the crowd in the row in front of me, and they were absolutely animated. I was amazed by their enthusiasm, and I didn't recognize them. This is obviously before selfies, so you didn't often know what the famous people in the field looked like. And I turned to the person next to me and I said, "Who are those two guys?" And the person said, "Oh, the one on the left is Jim Mitchell, and the one on the right is Harry Seed." And that immediately just stuck with me. I said, wow, those two giants, to see them so excited and animated, they were sharing the results of some tests that they had performed. And so that actually stuck with me, and it made me always realize that what I portray out directly and indirectly can be so important to others in the crowd and in building enthusiasm and excitement for our field. So having said that, I would like to, this seems to need two pushes. maybe 3. All right. So if somebody were to say to me, though, so what's really the motivation for the topic that you've picked? Well, maybe the romantic answer would be that early in his career, Professor Seed did research and wrote a paper with Lyman Rees on the topic of the action of soft clay along friction piles. And it was published in the Transaction of the American Society of Civil Engineers. In fact, that paper was one of that was included in the list that Jim Mitchell put together as part of the National Academy's biography of Professor Seed. And so it'd be nice to be able to say that that was what ignited my interest in interfaces. But the reality is, okay, is there something needs to be done with this? Because I have to push at least twice to get it to move forward. The reality is that in 1986, I took a class with Bob Holtz on geosynthetics. And that's not to say that that's a second-tier opportunity, but let me explain. Bob was talking about interface friction, and in class I said, he was mentioning the fact that the interface, you could probably get about 65% of the soil friction was a good number to use, and he was referencing what was being used in practice. And being the obnoxious graduate student, I raised my hand and I said, Professor Holtz, what do you think the maximum we could get out of an interface was? And Bob thought for a little while, and then he said, well, depending on a number of factors and considerations, maybe we could get 75 or 80%. And at the time, I said, thank you very much. But therein was born the question for me was, why the hell can't I get 100%? If I'm an engineer, I surely should be able to get 100%. Well, of course, there isn't a simple answer to that. Although today, if students ask me, what's the most I can get out of an interface? I will tell you, oh, probably 120%, but the problem is, if I get you 120% at the interface, the failure will move into the soil, so the maximum you can actually get is 100% of the soil. But nonetheless, there's a big difference between if we're willing to accept 70% or we can get 100%, then I think it's important that we stop and think about how we can achieve that. So, interfaces are ubiquitous in geotechnical engineering. You all know these, but just for context, they're in lab tests. Some of you may be looking a little bit at why is the Casa Grande dish there as an interface test? That's how it operates. It's a curved brass plate with soil inside it, and you're actually measuring the rate of closure of the clay to the groove at the center. It's an interface test. Lubricated end platens is another place where in lab testing interface friction can be very important. It can affect the shape of the specimens, for example. And finally, obviously, we can actually intentionally perform direct shear tests, interface shear tests as part of it. If we move to the field, then obviously we have things like the cone penetrometer with a smooth sleeve. And I'm sure we're going to hear a lot more about cones on Tuesday night with Paul Main. But also there's a Iowa borehole shear device, which was specifically designed to try and determine in situ interface friction. And finally, every time we put a soil anchor in the ground, we have to run an interface test, either proof or performance, to assess the pull-out resistance. And finally, geostructures, and as you can see, I've got a pile foundation system, I've got soil nails or other retaining walls, I've got geogrid reinforced soils. All of these involve interfaces, and so it is no exaggeration to say that I'm not sure there is any geotechnical project out there that hasn't got multiple interfaces in it, at least involved somewhere between the lab, the field, and the lab, field test, and the actual prototype structure. So let's move on then to a little bit of sort of more specifics. If I start to think about idealized single particle geotechnical interfaces, first of all, here is a circular particle on a smooth surface. And if you look at the dashed line in the center of the graphic, you can see that it actually, there's no up or down movement of it. I would argue that that circular particle is actually quite compatible with the underlying flat surface. If I go from pure rolling to pure sliding, you'll see that it actually looks remarkably similar. Trust me, in the GIF, those particles on the right are actually not rotating, but the bottom line is there's a similarity between those two. If I move on to a square particle, you can see that as long as I design a surface for it to roll against, and this is the pure rolling case, you can see that again that centroid line does not deviate up or down. So there is a degree of compatibility there, but if I go to pure sliding, now you can start to see that that particle centroid line fluctuates up and down. However, if I rotate that particle 45 degrees, guess what? I actually can get rid of that, even though it's now a rough surface with a square particle. So the bottom line is all of those single particle idealized systems are clear evidence that interfaces have different compatibilities. And of course, the reality is that actual geotechnical interfaces fall somewhere in the milieu of all that. There is rotations, there's rolling, there's sliding, they're moving relative to smooth surfaces, they're moving relative to textured surfaces. And so it is really a very complex. Real interfaces are much more complex than that. There are two important bilinear plots that I always talk to students about when I'm talking about interfaces. The first of those is this research that was originally presented by Yushugi and Kishida, some Japanese scholars in the mid-80s, where they plotted the relationship between coefficient of friction and surface roughness, or normalized surface roughness. And remember now, they are now looking at real systems, so the particles at the interface are not only interacting with the interface, but they're interacting with the particles right behind them. And so there's a much more rich environment for things to happen. What was important was that prior to this, interfaces were really referred to as smooth, slightly rough, and very rough. And so it was in that qualitative world that it made it difficult to sort of extract more out of it. As soon as this was presented, it became very clear that actually quantifying roughness of surfaces is a very important thing to do. And if you start at the left-hand line, at the edge of that line, at low normalized roughness, that's, for example, going to correspond to a smooth surface with particles, and they're going to slide next to it. In fact, to be honest, the particles barely know that they're moving relative to the surface, the smooth surface next to them, aka CPT, smooth friction sleeve. It's a slide-by test. In contrast, as you increase the roughness, you can see there's an increase in the friction as a function of normalized roughness up until some value. And at that particular value, then you reach a critical roughness where the failure actually moves into the soil, because what now happens is particles get trapped in the rough surface, and once it's sufficiently rough, then it becomes a soil failure system. So the bottom line is here's where I can argue I can get the 100% rather than the 60 or 65%. The second bilinear plot, which is also very important, and this is showing the relationship between the log of peak friction coefficient and the log of normal stress. And many of you may have seen this at various stages. But at low normal stresses, you will have a certain value of peak friction coefficient. As you increase the normal stress, you actually see a decrease in the friction. And it continues to decrease. And in fact, that's the slope of that line gives you the exponent of the Hertzian contact law. And what is happening there is that even though the normal stress is going up, the number of particles that are migrating to that front row are actually increasing. And so the contact stresses are going down up to a certain stress level. Once you get beyond that stress level, then one of two interesting things happens. The right-hand end of that solid line goes horizontal, and what that means is that the front row is filled. There are no more locations for particles there, and the relative hardness of that surface is such that it remains a sliding mechanism. However, if I have a softer surface, maybe instead of steel, for example, I have a polymer, then what starts to happen is, as I increase the stress, I'm going to find that you get plowing into the surface as you're as your particles are moving relative to it, and or if you've got an angular particle, that may the orientation of that plowing line may grow up. Now, that not only applies to sands, for example, and let's say smooth surfaces. The same thing happens if you have a geotextile and a geomembrane, and we have generated plots similar to that. I won't be able to show those today. So, against all of that and the motivation and the context, the lecture outline, I'm going to talk briefly about some factors enhancing or limiting compatibility. I'm going to give you brief insights from a few past studies, and then I'm going to move on and take a little bit of a look at some microscale interactions using DEM, some alternative thermal interfaces using coupled EFM, because actually one of the important things is that interfaces is not just about structural performance. Increasingly, thermal performance of interfaces is something that we need to be looking at. And then finally, I'll end up with a few examples of some ongoing and new inspirations for geotechnical interface design. So, here is a long list of factors that are enhance or limit the compatibility of two materials adjacent to each other at an interface. I am not going to talk about all of these because otherwise we'd be going for dinner just in time to get to the Terzaghi lecture, but there is a huge rich field there, and you will have additional information on this in the written version when I get to that. However, I will say that over the years, as we've been studying interfaces, we have picked off just about every one of these through a particular study to try and understand how important is that. Some are more important, some are not so important. That's good. All are relevant. More importantly, as I stand here today, I cannot tell you if them being more compatible or less compatible is always good. And you'll see that from some of the examples that I do. It might be nice to think that, oh, if I make it more compatible, it'll be better. But that, from an engineering point of view, may not be what we actually want to get to. So, looking at some insights, and I've already mentioned the multi-friction sleeve penetrometer that we developed a number of years ago. We didn't want to fight with the CPT people, so instead we added an attachment with 4 smooth friction sleeves behind it. That was the first embodiment of the apparatus. And when we did that and we pushed it into the ground, this had 4 smooth sleeves, sequential, one above the other. But if you actually look at the friction sleeve stress versus depth, it essentially looks like there's only one line there. And that's because even though it's a staged test, the fact that you had another smooth sleeve following the first one made no difference to the soil. It hadn't been affected by the first one. So whatever response you got from the first one, you got the same from the second, the third, and the fourth. In contrast, when we put a sequence of sleeves going from smooth to sleeves with increasing roughness, now you can see that we actually generated different friction sleeve profiles versus depth. And I'm glossing over lots of details here, but this early work was the work of Jason DeYoung's PhD, for example, and we spent many, many months looking at patterns so that we could avoid clogging, for example, with these sleeves. Here's an image of just some of those different sleeves that we used, and you can see that there are smooth sleeves there, but there are some with textures of different magnitude or different roughness. And in fact, we also did tests where we only put textures on a small portion of the sleeve, and no surprise, you didn't need the full-length sleeve in order to get the same measurement of friction, because the only reason the sleeve length is the length it is because that's what it was originally needed in order to have enough space to put all the electronics 50 years ago, 60 years ago. So that became a very useful. Probably most importantly is this was the bilinear plot that we generated, not in the lab, but in the field. And so with a single sounding you could actually generate this bilinear relationship in the field, showing the relationship between interface friction or shear stress and normalized roughness. Other studies that we did in the lab, we were interested to see, so what is happening at the particle level as we move away from the surface of the sleeve. In the upper plot here, the sleeve in this case would be in a vertical direction, and this is an image showing some sand particles to the side of that. We made detailed measurements of the void ratio, and the line in the lower plot is actually showing you the as-prepared void ratio as a function of distance from the sleeve face. We've also plotted there, just for reference, E-min and E-max for this particular sand. So this would have been a pre-shear. When we sheared the sand particles, this is what we found. And you can see that close to the sleeve, up to about 4 millimeters from the sleeve, we actually had dilation. And then outside, for probably the next 4 or 5 millimeters, we had slight contraction, and then essentially we went back to what the original condition was. So there was this zone of probably somewhere between initial 4 dilation, the next 4 mild contraction, and then beyond that the sand was unaware of what was happening in the system. When we, instead of moving the sleeve axially, we rotated it torsionally, we found the blue line. And now you can see that the dilation was still similar in the same region, but now there was a much larger zone outside the sleeve where we were getting contraction, and in fact significant contraction. And so we complemented these experiments with discrete element modeling. By the way, this was the PhD work of Alejandro Martinez. And what you see is that the particle movements, depending on whether you're moving the sleeve axially or torsionally, are completely different. In one case, they actually stay very close to the sleeve, whereas in the other, they're actually thrown off at tangential directions, and that has an effect on the performance. By the way, it also has opportunity. If you're thinking about what's the implications of that, for example, for piles, perhaps based on the installation of piles, you may be able to get superior performance. And finally, this is just a graphic showing those relative differences in the volume of soil involved for the same sleeve, the same sand, but just by changing the direction of relative movement. We've also done work with shear bands, and you might say, well, why shear bands? Aren't we talking about interfaces? Well, a shear band is actually 2 interfaces back to back with the same material properties on both sides of the interface. And so in a biaxial shear test, we captured specimens. We then used resin impregnation and image processing to generate slices from the specimens that we captured. And we had this concept that depending on where we captured the slices relative to this particular cube, and I'm showing a schematic with a shear band diagonally across it, that for surfaces on what I call the A or B faces, that's the front face or the top face, there's always the same proportion of soil within the shear band as well as outside the shear band. So while I may get some local fluctuations in the void ratio in the slices, I shouldn't see much different. In contrast, for the C slices, in other words, if I start at the one end and slice through it, you can see that there clearly seems to be some kind of a signature where, because the percentage of those slices that are initially not in a shear band, then partially, then fully, and then partially, and then not in a shear band, varies as you go from one end of the specimen to the other. Here is the results. This is actually for an unsheared real specimen. And while there's a little bit of fluctuation in the early part of the A sample, you can see that the rest are essentially, as we had hypothesized, fluctuating above and below that median line. The other thing that's interesting to notice is that I put to scale the circle there showing the particle size that we used here. And one of the things that emerged from this was the recognition that if you have a relatively uniform sand, then obviously the void ratio structure that emerges from that, even over a large representative volume, is going to be influenced by the presence of those particles and the diameters of those particles. We repeated the exercise for a sand sample after shearing, and as you can see, while there's obviously more natural fluctuation in these, the results actually mirror the hypothesis of what we had shown. So the bottom line is that this was showing us how there are other measures of what's happening adjacent to or in shear bands that are important for us to take advantage of. Moving on to geosynthetics interface testing, and again, there were multiple PhDs that did work over the years, so I'm just going to show a couple. But this is 3 different geomembranes and the same geotextile. And as you can see, everything else was the same, the normal stress, everything else. I've just referenced these as smooth, slightly textured, and moderately to heavily textured geomembranes. But you can see that essentially the backbones, the curves, the inertial early parts of the curves mirror each other, but there's a different peak strength and a different post-peak response as a function of the texturing of the geomembrane. In contrast, if I use the same geomembrane, and I don't mean repeat test, I'm still using virgin geomembranes, but of the same geomembrane and a different geotextile, now you can see that there's a big difference both in the peak strength, but also in the strain or the displacement of peak strength. So again, there's an important relationship of the other side. It's not just about the roughness of the geomembrane, it's also about the unit weight of the geotextile, how thick the geotextile is, and so on. Lastly, with respect to geomembranes, we've done a lot of testing where we tested elevated temperatures, because a lot of times we only test at room temperature in the lab, but then we put these into liners in landfills where the temperature may go up to 65 degrees, and so we were interested, so what's the effect of that? We did it with many different types of geomembranes, typically against a needle punch non-woven geotextile. The one on the left is a smooth, the one in the middle is co-extruded, and the one on the right is structured HDPE. And other than that, everything here in all of these tests was similar. And so you can see that there are dramatically different stress-strain curves exist for those interfaces. The other thing that I will point out is that is quite fascinating, and that is if you look at the post-peak portions of the structured HDPE, you can actually see there's sort of a periodicity emerges in those. And that's reflecting the actual interactions between, for example, the spikes on that structured geomembrane and the geotextile. One of the nice things about testing geotextiles is that you see the same behavior as you do with sands, but it's actually much nicer because, first of all the particles are the same diameter, maybe 35 micron filaments, and they're long, but you have many more contacts, many more points of contact as well. And so you actually get much richer, much nicer curves when you do those tests. So again, I'll make the argument that elevated temperatures influence the interface compatibility. Now, the good news here was that with higher temperature, you're getting higher strength. So you don't need to go and worry about the landfill that you designed with a friction value based on room temperature. I'm not making any comment about what happens if you put the liner in Canada and haven't tested it at 0 degrees. We also have done studies where we've been looking at anchors and pull-out studies. We looked at both fairly rudimentary control branches, but then we started 3D printing in branches as well. We did pull-out tests both in the lab scale but also in a CT so that we could actually see what was happening around the specimens. And here is digital image correlation of one of those tests, and you can see, for example, how there's a very nice shear zone forms. This is for shallow where we've got a breakout occurring. We also did digital volume correlation, so that's for the same results. And you can see a very nice cone that evolves there, and you can see where the individual branches actually poked out through the bottom in these particular specimens. One of the reasons I wanted to show this was that by looking at those images from the DVC, and it's represented in the plots in the lower right here, the upper one is a 3-branch at 30 degree, and the lower one is a 6-branch at 30 degree. But you can actually see how arching is varying as you go from the near radius to the further out radius. So arching is an important factor in interfaces that we need to be taking care of. And I think this is my last insight slide, but we've been also looking, and many people have looked at doing triaxial simulations with whether it's FEM, DEM, or physical experiments with geogrids placed at the center of specimens, different aggregates. And so for the particular study that I just wanted to share here, we looked at 4 different geogrid configurations, the original biaxial and then triaxial types. The third one from the left here, or the second from the right, that's the new Interax. I say it's new, it's out now on the street, probably a couple of years that Tensar produced. And then there's one on the right called SpiderAx 1, which is a different configuration that we've been playing around with in our studies. Here are the results of the deformation of those specimens. I've normalized both 1-to-1 and 2-to-1 specimens here, which is why they all appear to be the same height. In the plot on the left, we put the geogrid at the 1/3 point. In the middle, we put it at the middle plot, we put it at mid-height, and in the lower plot, we put it at the bottom 1/3 point. The leftmost line, and I apologize, there's no pointer provisions up here, but the leftmost line is the unreinforced, in other words, soil only, whereas the others show the different geogrids and the different relative performance. The important thing here is that keeping everything else the same but changing the geogrid, you're going to get a different interface friction response in this system, and I think we need to pay more attention to what we're doing there. So then, as a result of that, I'm just going to spend a few minutes looking at some what I'll call microscale aggregate geogrid interactions. So this is a schematic of work that we've been doing. Rod Barela is the PhD who's been doing that. By the way, I should have mentioned the previous geogrid work was done by several students, Andres Peralta and Janda Schoner. So many of them are in the audience, and I wouldn't be up here with the opportunity to present this wonderful research without their help. In this particular case, we were doing 2D clumps using YADE. You can see the geogrid in the middle of the specimen there, and we did cyclic loading of the specimen. For the part that I want to present to you today, we looked at 3 different configurations. On the left is a sample that is unreinforced, and the concept was that would be likely the one that would give us the largest rutting or the maximum deformations in the system and so on. In the middle, we have maybe what I might call a conventional geogrid situation where, irrespective of whatever the structure, the in-plan structure, the geogrid is, that's what we're currently using. And then in the right was a very interesting approach that Rod came up with, was to actually, within the DEM, to restrict lateral translation of the particles in a certain zone. And that was intended to sort of give you a lower bound to what deformation you might still expect to see. You couldn't get less than that. And so we did simulations with all of those. Here are the DEM force chains. On the left, you can see the unreinforced, and for those of you who use a 2-to-1 stress distribution, that might give you a little bit of comfort. But you can see that in the middle, where the presence of the geogrid is obvious there, you can clearly see how there's a pinching in of the deformations there. Now remember, we only, in all these cases, you're not restricting vertical deformation. What you're doing is trying to provide lateral confinement at a particular particular elevation. And then in the right is the one that we would call was perfectly reinforced. And again, we're not restricting vertical deformation, so that's why you still see force change below where that zone was, but that becomes important. The plots here show the results of that more explicitly, and you can see that in the left-hand plot, which is what I'll call the rutting performance. The soil on its own is the lower plot. The upper plot is the artificially confined zone, but where we used a thickness of that zone of 1 times the particle diameter. And then the line with the dots, that happens to be the old triaxial geogrid, so you can see it somewhere in between. And then the other 2 lines there are where we varied the thickness of that artificially confined zone. And we could see that if we had a confined zone of 0.1D, it actually did very little for the confinement. So a coarse aggregate with a conventional thickness geogrid probably is not going to get you what you're hoping to get because you're not causing that interaction that you're looking for, that compatibility. The horizontal displacements are presented in the middle plot, and again you can see that there are the relative performance when you have unreinforced versus triaxial versus the 2 plots towards the left are where you have 0.5 and 1 times the diameter of the particle layer constraint. And then finally the vertical displacement. And as I said previously, we were not trying to constrain the vertical displacement, so while there are some minor differences, those all are closer to each other. We looked also at, for example, things like the force network distribution. And in this example here, there are 3 different geogrid geometries. The upper one is triaxial, the middle one is a biaxial, and the lower one is a hexagonal. And you can see that the darkened color areas in the middle are reflecting the forces that are in those various grids within the system. If I just determine the normal rib axial force, in other words, the force in the direction perpendicular to the loading, then these are the values that I get. This plot is showing what those forces are as a function of distance from the center. So right at the center, you've got the higher forces, and as you move towards the periphery of the sample, the forces essentially diminish to close to 0. If I, instead of plotting those as individual values, I plot them as cumulative force plots, then you can see that the blue is the hexagonal, the green is the biaxial, and the orange is the triaxial. And what you can see in this case is that just changing what the structure of the grid, everything else is exactly the same. Again, I'm now getting a much different response where with the orange triaxial in this case, I'm getting a much greater distribution of the radial forces away from the point of application. So in other words, it's involving more of the geogrid in absorbing the energy that's being put into the system. Similarly, we looked at the rib axial stiffness. So in the last one, they were the same stiffnesses, but we changed the thickness of the layer. In this case, we're looking at the rib axial stiffness. And in this case, I did not change the geogrid, so these are all a triaxial geogrid. And this is the individual rib axial force plot, and this is the normal cumulative axial force plot. And again, you can see that while there is still some influence, there's not anything like the amount of influence. And in this case, we changed the ribs from 1/10 to baseline to 10 times baseline. So a large range of stiffnesses were looked at in here. So as you're thinking about what you might want to put as the properties of your geogrid, you may well, at least on the basis of this, want to be looking more at the geometry rather than the stiffness of the ribs. Lastly, moving on to alternative thermal interfaces. we're all very familiar with some of the excellent work that's been done in the last decade or 15 years with thermal interfaces. The particular plot I have here comes from the work of Olgun and McCartney. And I would argue that I think taking a structural pile and adapting it to add in a thermal component has been well developed and utilized. However, being the ultimate questioner about interfaces, I said, could we do a better job at the interface? Because in fact, what you have there is, sorry, this thing has taken off on a mind of its own. What you have there is you've got fluid in the circulation pipe, then you've got the grout or concrete, and then finally you've got the surrounding soil. And so in the fluid and in the concrete and the soil, you have conduction and convection. Radiation is limited. So we did some COMSOL multiphysics studies on that. This was the PhD work of Victor Attalay, who's also in the crowd here. And this was, we validated our model using the thermal response test results from the researchers shown in the bottom there. But this was where we said, well, so what could we do differently? And so we came up with the concept of what I call an engineered thermal transition zone. And the idea here was let's not focus on the performance of existing systems, but is there a new system out there that we could perhaps introduce and do better with? And so very briefly, this is a plan view across a structural pile in the center in blue. We're calling it some kind of an engineered thermal transition zone around that, and then we have the surrounding geomaterial. For want of a better word, that pink area, our goal there was can we augment the thermal properties of that so we can actually get more out of the same pile system. There are some other factors that were also of interest to us. For example, when you start adding fluid loops inside a concrete pile that's got lots of structural steel there, it gets busy. And in fact, you're sort of impinging on the structural neighborhood. And so part of our concept was, are there other ways that we can change the circulation loop systems? So in this particular study, this is still a numerical part of the work, we looked at two configurations. One was the baseline, but notice that our baseline, we used a 75-meter long conventional pile, conventional heat exchange pile with a single U-loop. And then in the lower one, we used an engineered transition zone, and instead of trying to put the loop inside the concrete pile, we actually used a spiral loop inside the engineered transition zone. And when we did the COMSOL simulations on that, here are the results. The lower blue line is showing you the power that can be extracted with the single loop system in a 70-meter long pile. The orange line shows you what we were able to extract with the spiral loop in the engineered transition zone, but only for a 30-meter long pile. So we actually reduced the length of the pile by more than 50%. And then finally, the last part of the example of the results that are shown here, the gray lines show what happens if you actually run the system on an intermittent basis. Turn it on for 24 hours, turn it off for 24 hours. In other words, allow the thermal zone to recover. And just like we learned from our friends doing pump and treat in the environmental world, there are often benefits to not trying to run the system 24/7, 365, but rather using it intermittently. We did lab testing as well, and this is just a schematic and photos of the lab work. And again, here are plots that we got with the actual lab experiments. The blue line again is our baseline, and the other versions are either the baseline but with an ETC, or a spiral loop with no ETC, and the green line, which is the one that obviously allowed us to extract the most power, is a helical tube with an ETZ. So the bottom line is that all the results that we have generated so far are showing us that both the model and the chamber tests, we can do much better with heat exchange piles if we start to be creative and think about, is there a transition zone and an opportunity to do something with that? So, new inspiration for geotechnical interface designs. Should not come as a surprise to many of you that I'm going to show some bio-inspired inspirations. One might be, for example, snakeskin on piles. One might be tree roots for ground anchors. One might be spider webs for geogrids. And one might be bamboo stems for thermal exchange systems. The other thing, though, I think is very important is that we need to stop and think. Typically, we have approached interfaces as that I'm going to grab a piece of steel from my friend, the structural engineer, and I'm going to beat it into the ground, and I'm going to accept whatever interface that generates for me. And I'm not picking on the steel folks or anything like that. It could be just as easily concrete or timber or whatever else. But we don't actually think much about the face as we put it in. I think as we move forward, it's going to be important that we think about interfaces from several perspectives. One, is it a preformed interface? And if it's preformed, I have the luxury of actually forming interfaces, for example, in factories, in labs, whatever, and maybe not labs, but where I can control the properties to a certain design value. A term that I've not heard used before, but in situ formed interfaces. And guess what? Placing geogrid in soil and then putting more soil on top of it and then compacting it, that's an in situ formed interface. And so there's an opportunity to also take advantage of that, not just do all of the design based on somebody's gradation that they give you and then accept it, but rather to think about both of the materials that are going to ultimately be at that interface that you're going to form in situ. The third category is what I would call adaptable interfaces. Maybe we can start off with something, but then change the configuration of it in situ so that it's adapted to get a different performance out of it. And finally, I'd be remiss if I didn't also talk about thermal interfaces again, because as I've said to you, we have a tendency to just think about interfaces as structural systems, but there's lots of opportunity associated with thermal interfaces nowadays. The important thing too, though, is all of these different types of systems that I'm talking about embody different degrees of compatibility. So quickly, pre-performed interfaces, and this is work that Alejandro Martinez and his research group at Davis is doing. Obviously, Alejandro and I spent many years while he was a PhD student talking about textures and various things like that. But he's been doing some very exciting work from my perspective, where he recognized that the fact that the directionality, for example, of a snakeskin can be very important in that you can have one interface friction if you're inserting and a different interface friction if you're trying to pull out. And there's many applications where that can be important, not just in piles, but in soil nails and in geosynthetics. To do that, he actually got cadaver snakes and measured their surface properties, and this is just some of his results. And then most recently, he's been doing centrifuge tests where he's been installing model piles with different roughnesses, sort of conventional rough, smooth, and with textures both cranial and caudal. And then he's been comparing the pull-out forces and the installation forces. And the bottom line is that there is clearly a huge opportunity to reduce the effort to, for example, perhaps install a pile, but get a higher capacity out of it once you put it into performance. In situ formed interfaces, so we've already looked at these a little bit, but I wanted to come back and reinforce some of the later things we're doing. And again, these are just a family of geogrids, and typically when we look at geogrids, we either see white geogrids on a black background or black geogrids on a white background. However, when I color code them, and I realize these are obnoxious colors, apologies, but information jumps out at you immediately. And you can see how, for example, the biaxial, all the openings are the same size. Likewise, the triaxial, all the openings are the same size. However, InterACS, in my opinion, represented a massive step forward because there are openings of 3 different sizes there. And then finally, our SpiderACS has also got multiple sizes. If I draw the histograms corresponding to those opening sizes, and this is biaxial and triaxial, you can see that while they're different in size, 100% of them follow one size. If I go to the InterACS, though, now here's where I can see I've got 3 different distinct particle or grid opening sizes. And if I do SpiderACS, I'm showing 4 here. They're different. The larger one here has the higher percentage compared to the others. But there's another important thing again, because remember, we're talking here today not about geogrid design, we're talking about interfaces. And so a lot of times we install these. Here's a typical gradation with limits that you might be given by your client that says, here's the soil we're using. I want you to reinforce it or to install geogrids to improve the performance. And so to simplify that, I have drawn the histogram in bins for that particular material, and that's the plot that's on the right-hand side. And importantly, if I merge all of them together, now my question to you is, which combination of geogrid in either the upper or lower left or the upper or lower right is going to work best with the aggregate? And trust me, we're locked in with some of these gradations, but we're not recognizing the fact that interfaces are a 2-party business, and we therefore need to be thinking much more about which are more compatible. And that's actually a part of our ongoing work. As an example, the other thing, though, that has emerged from us looking at this, so these are those unit cells that I previously showed you that were color-coded. If I actually stack a bunch of unit cells together, now something else immediately steps out and hits you. The one on the left, you can see it's a uniform, even though it's now made up of 7 unit cells, it's still got a uniform look. And importantly, the connections between the various cores of the units occur at nodes. But if you look at the one on the right, what suddenly starts to appear to emerge, if you compare, let's say, the middle upper plot with the middle lower plot, there is a secondary structure starting to emerge once I start to look at the larger geogrid. And as soon as you realize that, you say, wow, I should have thought of that before, because, you know, think about our friends who in the steel business who make trusses. They don't make them out of one size steel truss. They use multiples, and they've got different configurations. They understand it, and they're not even trying to get it to work with soil. We have a much harder job because we're actually trying to get it to work with soil. So, and this is just to show, again, looking at some of the deformations. So my question is, and this is something that Jandash hears from me on a weekly basis, does the emergence of a secondary structure alter the compatibility and improve performance? Finally, adaptable surfaces. We've got a lot of work we're doing with root-inspired ground anchors. And of course, when we started, you know, the big question was, well, that's nice, you've got these 3D printed ones, but how do you get those into the ground? Well, that's why you hire incredible graduate students who come up with great ideas. And this is the PhD work of John Huntoon, whose only shortcoming in life, by the way, is that he's an Oregon State Beaver, and so we had to re-educate him into a lot of things once he came to Georgia Tech. But this was an initial model that John made. And then here's 3D printed. When it gets launched into the ground, it goes in an enclosed fashion. Once it's in place, then we can expand it out, and this particular one has 5 branches. We've actually done field tests with this, and that's an exhumed one in the bottom left figure. But importantly, if you look at the plot here, the conventional anchor, straight shaft anchor that we might use is in the lower plot, and the root-inspired ground anchor is about 75% higher capacity without changing anything else. And finally, the bio-ETZ piles. Again, we've looked at this engineered transition before. One of the nice things about looking at revisiting with this transition zone, we can actually separate the thermal and structural components. And in some cases, we may want a deeper structural component that can go down to a bedrock, but we don't need to go all the way to bedrock with the thermal component of it. And what we're actually starting to look at are these new structures that are bio-inspired, that in fact, instead of using augmented soil, we can perhaps use some of these bio-inspired structures. And in order to do that, here's sort of some of the conventional EZ piles that we've already studied, and here are some of the configurations that we're now looking at. And we're able to play with the structural capacity and the thermal capacity separately. So depending on, for example, in the bottom right, I'm calling that a structural hyperthermal pile if I really need a higher thermal capacity. So in summary, the properties and performance of both materials at an interface are important, both individually and collectively. Their opportunities for interface design innovation are abundant. We need to be willing to question some of our existing approaches and seek new inspiration that can lead to transformational, not just incremental changes. A test for me at times is this going to give me 5% or is this going to give me 50% or is this going to give me 100%? I'm much more interested in the 50s and 100s because that way I think it makes it an easier sale for me when I'm working with industry to convince them of the value for them also. Certainly something that I think has been missing both in research and practice is questioning how compatibility can improve interface performance, and I think that's a critical factor going forward. We have all the necessary tools, experimental, numerical, visualization, so we're not lacking there. And what I've tried to do in this lecture is to illustrate this with a couple of examples, but as we say in the face of today's climate change, this is only the tip of the iceberg. So I'm going to leave you with a one-slide recap. I began this lecture by noting that H. Bolton Seed studied pile soil interfaces early in his career. With tongue-in-cheek, I have to tell you, the Alaska earthquake came along in 1964 and distracted Professor Seed for the next 40 years as he created the field of geotechnical earthquake engineering. And there is, I know, huge number of you in this room who worked with him and benefited from his activities in there. Interestingly, however, when you start digging around and you're trying to think about how am I going to tie all this together, I came across a short presentation that his close collaborator and friend, Professor Idris, it was at the Second International Conference on Geotechnical Earthquake Engineering and Soil Dynamics. And Professor Idris, in his lecture there, reminded us that in Dr. Seed's 1979 ranking lecture, he wrote, "It is extremely important that we take every opportunity that nature provides to continually refine the procedures." Now, I realize that he was talking about earthquakes so that they can refine the procedures. But you see where his mind was going. Nature is a wonderful tester of things that we do. In fact, it's a wonderful source of inspiration. And so, hopefully, I have filled in some of the gaps linking Professor Seed's early work on interface while respecting his vision for the role in nature of what we can do with interfaces. And with that, thank you very much. The contributions of teachers, discussions, students, colleagues, all been a pleasure to work with, obviously very important. I put a list here of people that I think I would like to especially thank. I gave them all initials, so I'm sure everybody's going to be looking for the slide to see, did he put my initials in there? And if I didn't, it's an omission and I'm to blame for it. And finally, thanks to the ASCGI for the honor of selecting me for the honor of receiving the Seed Medal and delivering this lecture.